All right, here we go. Last topic before, I guess, last topic in steel. Okay. And what we're going to talk about are steel columns. I think you're gonna like steel columns. They're not too bad. Okay. There's a lot going on, but the actual design process isn't so bad. Um, Announcements, right? What do we got? We got this Friday, the lab final. Okay, I think Jaden posted a study guide online. Right, you're gonna take it on D2L. I asked him to set it up so that you could take it anytime on Friday, but once you start, you'll have 1 hour to complete it. Right? Is it hard? I don't think it's super hard. I think that as long as you study, you're going to be fine, right? There's no major tricks or anything that associated with, but you can't just go into a cold turkey. You do have to do a little bit of studying in order to go from there. So that's about it there. I'm gonna assign a homework probably tomorrow on Tuesday. It'll be due on Friday. It typically is not too bad. I would like to do, our final is scheduled for next Thursday. I'm planning on just sticking to our regular final time to take the exam. Um, I haven't really worked that out yet. I haven't decided if we're going to do a take home or not. I'm leaning towards maybe yes, but stay tuned for the details associated with the final. And also, I wouldn't mind doing a little review again, like we did last time, where we all get together and see each other one last time at least. So, and then also in the next day or so, I went to the university today and I picked up your lab reports that were given to me, and I'm going to scan those suckers and send them your way, and you just have to make the edits on those. Okay, so let's get started here. Okay, so columns, right? That was my impression of the guy from Lord of the Rings. Gollum. I think is his name, right? Gollum. All right, columns. Chapter E. All right, so where are these things at? They're all over the place. Okay, they are right columns in your code. Okay, and so again, you're gonna want to go through and tab these sections. Chapter E is the specifications. Right. Okay. Chapter E is the specifications. Table CA 7.1. This coming out of this one's kind of hard to find. This is in the appendix. This is actually in the commentary. That's the C of Appendix 7, and it's in the specifications as well. Okay. It is in the specifications, but what it is the effective length factors, which we're going to get into in a little bit. Okay. Table 4-1 is a design aid. Okay. And B4, this right here, it tells us if we have compact sections or not. All right, we're not going to use that section too much. And by too much, I mean not at all. Okay. And so we are, however, we're going to use chapter E. We're going to use this commentary in the appendix to figure out what these effective length factors are. And then table 4-1 as well. But my handwriting is particularly bad this evening. And just got done lecturing a couple lectures for dynamics. And I think that is making it even worse. Okay, so that's it. The other thing we should mention here is we are only going to do axial load. Right? We're only going to look at axial load and no bending. Okay, we're only going to look at axial load and no bending. right? We don't have to worry about the interaction between bending and axial load. We go into grad school, absolutely. A lot of your members are going to have axial load and bending on them at the same time, but we're just going to go straight axial load. Okay. And so the way we've done all of this steel design thus far is we start out talking about the limit states that control design. Okay. The limit states in this particular case, I'll type these things. Limit states are going to be yielding, right? That's typically always a failure mechanism in steel design. That's typically how we want these things to fail, is due to yielding, because there's lots of warning. Okay, yielding is one limit state that we have to worry about, and then global buckling. Right? This is similar to lateral torsional buckling, but different. Right? Lateral torsional buckling was just the compression flange buckling out. Okay, and in this case, global buckling is the whole member buckles, right? And it's either going to buckle around the weak axis or the strong axis, but we're going to get into that a little bit later. Okay, but that could be a failure mechanism as well. But then you could also have local buckling. Okay, and we're just going to stop this one right here. This is not an issue for most sections. Okay. That's not going to be a limit state that we have to deal with, right? This is very similar to, lateral torsion or local flange buckling or local web buckling. AISC is no dummy, and they've designed the members in such a way that you're going to get yielding before you get local buckling, okay? And so I just want to make that note. So we're not even really going to look at that failure mechanism, right? If you have compact flanges and compact webs, then you don't have to worry about this, okay? And that's where that B4 section comes into play, is it comes into defining whether or not you have the AISC is no dummy. Most of our wide flange sections, this is not going to be a controlling issue, and so we don't have to worry about that, okay? And so what this thing looks like, again, you could have a curve just like this, and we're going to dive into this a little bit more, right? You can have our axial load capacity, phi(PN), and on this axis, and then in this case, you have to have some slenderness ratio, and in this case, for buckling, it's going to be a thing called KL over R, and we're going to get this. We're gonna. I mean, obviously, today's lecture we're going to dive into what this actually means. But this is how tall it is, how effective tall it is, and R is the radius of gyration. So it takes into consideration how stocky the member is. If the member is stocky, right, this number is less, and so you're over on this region over here. If it's really long compared to how stocky it is, it's going to be over here on the right, okay? But if it's stocky compared to how long it is, you're going to be over here on the left. If it's stocky compared to how long it is, then you're going to have the yielding is going to control your failure mechanism. So this right here is going to be yielding, okay? And then in here is going to be buckling. There's a couple different forms of buckling that can control, but it is global buckling. We should write that. That's global buckling. Okay, global buckling is going to be in that region there. As it becomes more and more slender, the capacity goes down. Okay, as it becomes more and more stocky, the capacity goes up until it hits the yielding capacity, and it kind of peaks out at that. Okay, and so we're going to talk about, well, how we calculate yielding, okay, and then how we go about calculating global buckling. Okay. Okay, so I guess the first thing to do when we get into this is we're going to talk about buckling in a little bit more detail, right? This is something that is oftentimes introduced in mechanics and materials. I don't think you guys get there in your mechanics and materials. I know when I've taught mechanics and materials before, we barely get there, okay? And by barely, I mean we don't get there at all, okay? And so if you're to see buckling at the very basic level, okay, they start out by introducing it with this little, typically they'll start out with this little contraption here. With this contraption here, we have an axial load, okay, applied to this thing. And this is just a rigid element with a hinge right here in the middle, and then another rigid element and a pin on this side, okay? And so this thing can deflect like this. Right? It's going to be rigid, okay? But it can deflect like that because there's a hinge right here in the middle, okay? But then if you were to deflect this thing, then you have this spring right here that wants to pull it back into place, Okay, and so the way the book, kind of, or how Mechanics of Materials works this thing out is what you're trying to figure out is how much of an axial load can you put on this thing, right? How much P can I apply to this thing before it actually fails? Okay, and the way they do this analysis is they come in and they say, okay, I'm going to apply this axial load like this. Okay, and I'm gonna imagine, and you can imagine, right? If as long as everything is completely concentric, this lines up with this down here, and there's no lateral displacement right here. As long as everything's lined up, the thing is totally stable. Okay, but what you do is you imagine somebody coming in and tapping this thing from the side. So you're loading it up like this. You're loading it up, and then you tap it from the side, and so this thing displaces a little bit. Okay. Right? And then what you'd look at is to say, okay, if I remove the tapping, right? If I remove this lateral force right here, what happens? Okay. Is this spring enough to pull it back into the vertical state? Okay. Or is this load right here applied to it too much and this cannot pull it back into place? Okay. And that's the point where you apply the load and you can't pull it back into place. So if this thing displaces like this, right? And this is what they call that delta there. Okay. Right. And so in this case, you have a restoring force, K times delta is going to pull this thing back into place. Okay. But then on the other side, you have this moment, right? This pushing down like this and this pushing up like this, right? It's got a moment that's applied right here, right? Because you have this P load times that distance delta is a moment, okay? If this P times delta is bigger than this K times delta, right? Once you kind of work through the geometry and stuff like that, if that's bigger, then this K times delta isn't big enough to pull this thing back into place, okay? And when you hit that point where the P becomes so big that the spring can't pull it back into place, that's what we call buckling. Okay, and it's actually pretty curious is that once mathematically, if you were to work this thing out, and if you want, you can look up Mechanics of Materials book, but mathematically it works out where you don't have to tap it from the side, right? If you apply the load like this and this, even if everything is concentric, mathematically it comes out that this sucker is going to buckle out to the left. You don't even have to tap it from the side. Okay, and so what do you get out of that? Well, I mean, what I want you to get is that there is this idea of this restoring force. You have this P times delta. You have this kind of moment that's applied because it's right. You could imagine this thing squishing, right? And then you have this displacement, right? There is this moment applied that's going to want this thing to pinch, right? And it wants to, if it pinches, right, it'll go like this, right? It'll start deflecting more and more, and the thing would collapse. But what prevents that from doing it is this spring that's there that kind of pulls it back into place. But anyways, mathematically, what it works out is that you come up, and I used to do this, but it takes quite a bit of time to demonstrate this. But what you get is this P critical. You come up with this value, P critical, KL over 4, right? When your axial load, and so that's kind of what, so this is the buckling load. Okay, that's the buckling load. And again, you get that by looking, I mean, really, it actually isn't too bad, but it's just looking at this geometry and looking at this restoring force. And anyways, a delta shows up on either side and they cancel out and then kind of demonstrate that it's going to buckle. But the point of this is if you calculate this is P critical, this is where it's going to buckle out. You calculate as that KL over 4. And then what you do is you look at your axial load, right? P is my axial load. If P is less than P critical, then it doesn't buckle. Okay, and it's stable. Okay, and so it's a stable. It's stable. Okay, but if P is greater than P critical, then it will buckle. Okay, and it would be unstable. Okay, or instability. That's actually a whole area of structural engineering. You're studying instability of things. But this is the idea. You calculate what the P critical is. If P is less than P critical, it doesn't buckle. If P is greater than P critical, then it is unstable and it buckles. Okay, and then this P equal to P critical is what you would call, it's kind of right on the cusp of buckling or not buckling. And then I just like to use this word. It's a bifurcation point. It's right in between buckling and not buckling. Okay, I just like to use the word bifurcation because it makes me feel smarter. Okay, and so it's just the limit between the two conditions, either buckling or not buckling. Okay, so that is in the most simple form how you can introduce buckling. Okay, related to that, right? We don't have cases like this, right? Maybe you have cases like this, but typically we don't have cases like this. We have continuous members. Okay, we have continuous members that are like this with no spring attached to the side. Okay, and this is what you may have seen in mechanics of materials. You might have covered Euler buckling. Okay, it's actually pretty interesting. Is this time of the class I'm actually teaching you guys buckling, okay, and it's got Euler out front, right? He had his hands in buckling. Those of you that took dynamics from me or have taken dynamics, at this stage of dynamics, we're learning about Euler moment equations for dynamics, right? He was just doing a little bit of everything. It's just kind of interesting that I'm teaching both of these Euler topics at the same time. Okay, so anyways, when we have continuous members, right, it's similar to this system up here, okay? It's just when there's no hinge in the middle and stuff. But when you apply a load, again, picture tapping this thing from the side. I'm going to move it, I'm going to tap it from the side, okay? And then we've got this load applied like this. And there is a restoring force that wants to pull it back into place. And bending is it, okay? Bending wants to pull it back into place, right? A member does not want to be deformed like this, right? So if you applied a little bit of load, tapped it from the side, released the load, the thing would snap back into being vertical, right? It would snap back into being vertical because it doesn't want to be bent, okay? Which is similar to this, K times delta, right? This spring doesn't want to be stretched, and so it pulls it back into place. The bending pulls this guy back into place, okay? And so what they do is they do something similar. Is they look at the moment, okay, this right here, how this is derived. Okay, we're not going to dive into it too much. We're just going to use it. But this is the moment due to the axial load, right? Okay, that's P times U. And so I should probably define what U is. U is this distance right here. U is a function of x. It's how much it's displaced from the side. And then this is axial load P. Okay, and so the way Euler derived this buckling equation is what he did is he came and he said, okay, this is the moment due to the axial load, right? P times this displacement right here gives me the moment to that location. And actually, you could come up with the moment at every location along the length of this thing, all right? And it says, right, if that P times U is the moment is a function of x, okay? And then if you remember back to your mechanics of materials days as well, the moment is a function of x. Like the bending component, okay, this is from bending. Okay, the bending component, right, a beam that's bending, okay, can be related to its deflections, okay? And it can be related to its deflections with this equation right here, right? This is back to mechanics of materials days, okay? This is from mechanics of materials. It's actually not too hard to derive this. I'll go MOM. Okay. We've seen this once before, right? That when you keep going with this thing, right, and you look at you're not just setting this equal to m of x. You keep going with this. You end up with EIU prime 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 is equal to the load applied, right? But along the way, right, you can also say that EIU prime prime is equal to the moment. Okay, we should probably make that clear that those guys are equal to each other. Right, and you may, just do you absolutely understand that step right there? Not super important, but just know that I just want you to like remember, right? Just think about it a little bit. You're like, oh yeah. I kind of remember that, okay? But that's it. EIU prime prime is equal to the moment as a function of x. And so what you do is you set EIU prime prime equal to PU of x, okay? Does anybody recognize what this is right here? Right? You got two derivatives of u on the right hand side, and then you got u on the left hand side, and you can imagine putting all these things on the same side. Okay, that's a special kind of equation. Okay, right? You even took that as a full-on class. Okay, and I'm waiting for you guys to answer this. Right, it's just a strange thing. Right now, I'm sitting in my bedroom drinking a White Claw. I'm trying White Claws out, which is pretty cool, and I'm lecturing to you guys, right? And waiting for you guys to answer. Okay, so here, this is a differential equation. I think somebody said that. Okay, this whole thing is a diffie Q. Okay, right? You got derivatives, and then you got a non-derivative, and you can imagine EIU prime prime minus PU of x is equal to 0. That's a homogeneous, linear, second order differential equation. Ooh, I like that. Just to refresh your memory, right? You've heard those words before. Linear, because there's no u's multiplied by each other. Homogeneous, right? Because it would be equal to 0, okay? And it is second order, right? And you get that by counting how many primes you see, okay? But so pretty simple. You said PU equal to the bending moment, right? That's when this thing would collapse or not, is when it's equal to that. Then you substitute in what this bending moment, you can relate it to its deflections with this equation, which we derived in mechanics of materials, and you solve this differential equation, okay? And that's what Euler did. He solved that differential equation, and when he did it, right, the cusp of the solution is this, right? This is, I guess we solve this with boundary conditions. Right, you may remember boundary conditions or initial conditions, right? BC's boundary conditions, okay? Because what I mean by these boundary conditions, right? There's different types of, right? If I had a pin and a pin right here, the thing would deflect like this. If I had fixed and fixed up at the top, fixed and fixed, it would come out and it would deflect differently, right? And so something fixed and fixed is going to buckle at a different load, right? And so you could put in those different boundary conditions, okay? And that's what he did. He solved this for a couple different boundary conditions, but in particular, the one of most importance is the one that's on the left here, is this guy right here. Our solution is going to be based off of that thing. So here's P critical. So this is the solution for pin connections and pin BCs. Okay, that's what that is. Okay, and Euler came up with this, and this you may have seen before. P critical is pi squared EI over L squared. Okay, and the other part of the solution, okay, is what U of X is going to look like. Okay, it is going to be a half sine wave. Oh, I guess I already wrote that. Okay, this is part of the solution, is that the shape is going to be half of a sine wave. Okay, part of the solution is that the displacement is going to be half of a sine wave. What do I mean by half of a sine wave? That shape right there is half of a sine wave, right? If you kept going with it, there's your full sine wave, okay? And so this deflected shape is half of a sine wave, okay? And so Euler came up with that. And so what does this say? Well, it says, well, if I applied a load, this load P, to my column, as long as that load P was less than pi squared EI over L squared, Okay, EI, right? So you can imagine your capacity is going to go up as EI goes up. So if my material's stiffer, then my capacity goes up, or if my I is bigger, my capacity goes up. But my capacity is going to go down if my L is bigger, right? If the thing becomes more and more, I guess it becomes longer and longer, it's going to fail at lower and lower loads, right? And that's easily, your intuition should be able to grasp that pretty easily, okay? And so this equation makes sense, okay? This is the restoring force, EI. L squared is how slender it is, okay? As I gets bigger or E gets bigger, your capacity increases. If L gets bigger, your capacity decreases. Okay, and so Euler came up with this equation. Beautiful. Okay, and we're going to see something pretty similar to this in the code. The code's going to look very similar to this. Okay, so those that's our Euler-Buckling equation. Okay, and it captures this effect over here. Okay, now what do we do for different support conditions or end conditions or boundary conditions? Okay, how do we handle those things? So this is to account for cases that are not pin-pinned. That are not pinned. I guess that is what the effective length factor is for, is to account for cases that are not pinned. Okay, we're gonna have KL is gonna replace L in buckling equation. Okay, and to get K, we look for half sine wave. Okay, and this is going to make more sense in a second when we look it down below. Okay, and so the idea behind this, okay, let me just take a step back, is right. Euler came up with this beautiful equation, right? This is what buckling is. Okay, right here. You could come up with the same equation, right? P critical for a different loading condition. I could look at a case where we used this before, a fixed. I could come back to this equation, right? And I could solve this differential equation, right? For different boundary conditions, okay? And this has boundary conditions. These boundary conditions are, we have zero displacement here, but we also do not restrain the moment, okay? In this case over here, we have zero lateral displacement, but we resist the moment. And so in this equation, when you solve this differential equation, you would vary what those boundary conditions are, okay? You could come back, and like I said, you could go back to this differential equation and solve it for fixed boundary conditions, and it would give you a P critical. Then you could come down and you could do a pin on one side and a fixed on the other. I could come back and I could solve this differential equation for pin on one end and a fixed on the other, and solve it with those boundary conditions, and I would get a P critical. Okay, and I could do the same thing for each one of these cases and get a P critical for each of them. Okay, totally valid way to do it. But what AISC does, they're no dummy. Okay, AISC is no dummy, and so what they've done is they said, you know what? All of those solutions for all the different boundary conditions can all use this same equation. But instead of using L right here, we're going to put this K out front. And that's the effective length factor that goes out front. And so really, it's just going to be the same equation. It's just we have KL there instead of L. Okay? And I guess we could just write that over here. So, yep, P critical is equal to pi squared EI divided by KL squared. Okay, and so the idea behind that is that instead of going back and solving that differential equation every single time, you could just use the same equation. It's just you change what that length is, right? Using this effective length factor. Okay, and so the easiest way to find out what that K is going to be, okay, is you look for the half sine wave, or someone did it, right? It turns out they've already tabulated all these things for all the different load cases, and they'll tell you what the K is, but I want to show you where they got it, okay? So in this case right here, right, so up here, this is the full pin. There's our half sine wave over that whole length. And in that case, K is equal to 1, okay? So then we come over here, and this right here is the overall length, right? I should probably put that in here. This is the overall length. Okay, and so you're looking for the half sine wave. So in this particular case, right, here is, right, a case right there. And so, right, sorry, this is part of a sine wave right here. Okay, now where do you find the half sine wave? Okay, this is actually a full sine wave. Okay, what you see right here, right? It starts out, starts out in this particular case, it starts out as 0. I guess that's how sine wave works. Starts at 0, comes up, and then comes back down to 0. So that's a full sine wave. And so you're after the half sine wave, you would catch it right in the middle. Right, there's our half sine wave right there, 0.5. Okay, so half of the length L is where we get our half sine wave. Okay, and so our K value ends up being equal to 0.5 in this particular case, right? Here's a case where we have pin and fixed down at the bottom. In this particular case, you get your half sine wave would be, where is it? It goes from here down to here, and that would end up being 0.7. Okay, in this case, right, so here's another one here where in this particular case there's no prevention of side sway, right? So in this case this thing can sway to the side. In this case it can't go left or right. In this case it can go left or right, but it can't rotate. You can see that block up there just means it can't rotate, and you can see over here it's not rotating, and so then this is what your deflected shape is going to be. But that happens to be half of a sine wave already. Okay, starts out at 0, peaks out at 1, right? And then it's on its way back down. I guess it's on its way back down, but it never does it, right? Or it doesn't get to that point right there. So in this particular case, the whole length gives us our half sine wave. So K is equal to 1. Okay, in this case, this is the pin, right? Obviously, that's where a half sine wave is, and so that equals 1. All right, so this is K is equal to 1, right? And then here, this one's actually pretty interesting, right? This is a quarter sine wave, okay? And so if you want to find your full sine wave, so this is a quarter, your full half sine wave is way down here, okay? And so in that case, right, your half sine wave is twice the length, okay? And so that your K value in this particular case ends up being 2. Okay, same thing with this one here, right? This one is a pinned on one end and a fixed on this side. And so then again, right, there's your half sine wave all the way to there. Okay, and so in that case, your K is equal to 2. Okay, if you don't quite see that, okay, that's fine. I don't know. You should stay low. It's not too hard to grasp there, but the idea again, they want to be able to use this thing. We're going to modify it. We're going to modify the length so that we can use the same equation. It's the same thing you would get if you solve this differential equation for the different boundary conditions. What you're doing again is you're looking for the half sine wave, right? There's our half sine wave in the middle there, and just the middle part gives us the half sine wave, and so our K is equal to 0.5. In this case, we have pin and fix. Our half sine wave is there, so that's 0.7. There is our half sine wave already, so K is equal to 1. Pin, K is equal to 1. Here's our half sine wave, and so we find that over 2 times the length, and so our K is equal to 2. And there, this guy's going like this, okay? Or you could think of it going like that, and so our K is ended up being equal to 2 for those. Okay, so then so this is straight out of the code. This is table CA 7.1, right? This is table CA 7.1. It's kind of hard to find it, tab it so that you can use it. Now, so this is the theoretical K values, right? But then underneath it, they say, okay, actually, you should probably, for design, are you going to have exactly these end conditions when you do a design? Not necessarily, okay? It's not going to be perfect. And so they say, here are some conservative values that you can use when you do design. Actually, not even conservative values. Here are the values. Oh, yeah, they would be conservative. Yep, that's bigger than this is bigger than that, that's bigger. And so for the most part, they're conservative values. And they say, yep, you're not going to have perfect cases like this, so use these values for design, okay? Then when you do your homework, right, I'll need to state which one you use, okay? The one for design or just using the other one. Okay. I think we've beaten that horse to death. Okay. All right. Now, so those are effective length factors that we can use in this equation. Okay. So that what we're building up to is what actually is shown in the code. Okay. So what you actually find in the code, this is going to be this guy down here, but we're going to get to there in a second. So this is the modified Euler buckling equation. Okay. So what the way you do this, okay, is you start out with this definition of P critical. This is what we had before, right? This is what Euler came up with, and we just added the effective length factor. You start out with that, but then you make the substitution of what I is equal to. So the moment of inertia is R squared times A. So in this particular case, right, this R is the radius of gyration. Okay, the radius of gyration, and then A is the area. And put equals there probably. Huh? Equals the radius of adjacent. A is the area. Okay, I guess that's the area of the steel member, and then this is the I is the moment of inertia, right? Right, the area moment of inertia, and so this is just geometry, really. Okay, how do you the radius? This is just a relationship that exists. You take the radius of gyration squared, you multiply it by the area, and it gives you the I. Okay, for some reason the ACI code likes to put this in terms of radius of gyration as opposed to in terms of I. I don't know why, but E is no dummy, and so they kind of want it in that form. Okay, so then they're going to take this and we're going to substitute that up in here for that I right there. Okay. The other thing that they do is for some reason they like to talk about the buckling stress as opposed to the buckling load. Again, I don't know why, but they want it in terms of buckling stress. So then what they do, so this right here is the buckling stress. Okay, they want it in terms of buckling stress. And so if you take the buckling stress and you multiply it by the area, the gross cross-sectional area, okay, it gives you the P critical. Okay, so what I'm going to do is I'm going to take this P critical and I'm going to divide it by A, and then we can solve for what FCR is. And so that's what we've done. Okay, we've taken this I. Actually, let's make that clear. We've taken I. Okay, we've subbed that thing in right there. That radius of gyration, and put the A up there on the top. Okay, and then we take this A and we divide it right here, right? So we divide by A. Okay, and when you do that and you simplify the equation, this is what you end up with. Okay, you end up with our critical buckling stress. Our critical buckling stress is equal to pi squared E divided by KL over R squared. Okay, and this is equal to this is in the code. The code, this is what it is in the code. Okay, we're going to see this exact equation in AISC. Okay, it comes directly from Euler buckling. They do a little modification to it. We'll look at it in a second. Okay, but we do see it, and I think that's pretty neat, right? You do this derivation, then you actually see that value in the code. I always find that pretty interesting. Okay. And then this is where, right, remember I mentioned right when we first started this, that's what our stress is going to be, or our capacity is going to be. Our capacity is going to be equal to this, and then what it's going to decrease with is this KL over R. And I can kind of see why they put in that radius of gyration. It kind of lumps all the section properties together. I don't know why they talk about it in terms of stress, instead of just keeping it in terms of P critical. But for whatever reason, it's historic, or whatever reason, that's what they do. But it's kind of nice that it kind of packages all of your slenderness stuff into or your buckling controlled properties into one location. KL over R is that one location. Okay, and so if you were to plot FCR as a function of if you plot FCR as a function of KL over R, it would be doing this, right? This is the buckling state out here, okay? But then if KL over R gets small enough, it doesn't keep taking off like this. It actually peaks out at what its yield capacity is. Okay, so this is kind of neat. So this is just a different way of writing Euler buckling equation where it's kind of tightly packed all of the things that control buckling into this one location in terms of slenderness and geometry, right? Elastic modulus is still going to control buckling, but it's up there on the top. Okay, anyways, so what does the code actually say, right? I said we're going to see this FE floating around, which we're going to see. There it is right there. So this is the code. So I just opened up chapter E3 in your steel manual, and I plucked this sucker out of there. Okay, and so what does the code say? So this is the AISC equations, chapter E. If you look at it, it says axial load capacity PN, right? And what we're after, keep in mind, right? This is always true. We get our PU has to be less than or equal to phi PN. Okay, and so this whole chapter E3.1 is about calculating what our nominal axial load capacity is. Okay, and so there's a phi that's going to be floating around that we need to put in there as well. So PU has to be less than phi PN. Well, PN is going to be this critical buckling stress multiplied by the gross area, just like we did right here. Okay, and then it says, well, how do I calculate the FCR, right? Well, we need to account for this part right here, right? The yielding right here. But then I also have to account for the buckling component. And so it's a piecewise solution. And so basically what it says, the critical stress FCR is determined as follow. When KL over R is less than 4.71 times the square root of E over Fy, okay? Or if this happens, which is the same, it gives you the same number, then your FCR is equal to this equation. Okay, when KL over R is greater than 4.71 times square root of E over Fy, then FCR is this value, okay, 0.877. I kind of like this equation because there is empiricism built into it, right? As a concrete person, I like to see empiricism. Here's some empiricism, right? 0.658. What the hell is that? Okay, 0.877. What the hell is that? It's empiricism. They ran a bunch of tests, right? They had this beautiful FE, right? This elastic buckling load from Euler, but it didn't actually model the things perfectly, and so they had to like put in this little fudge factor in order to make it work. Okay, so what does this mean, right? So this is kind of right of what's happening. If KL over R is less than this value, then you have this function. If KL over R is greater than this value, then you have this controlling. And so what that means over here, so this is where these borders are. It's somewhere in here. It's not perfect, but there'll be some place right over here. This would be 4.71 times the square root of E over Fy. Okay, that value would be somewhere in there. Okay, and what this guy right here. This is the equation that they came up with for plastic moment or plastic capacity. Okay. Or plastic capacity, right? It everything yields, okay, and inelastic buckling. Right. Before, when we designed for flexure, there were three different limit states for something that goes through lateral torsional buckling. Right. There was yielding, inelastic buckling, and elastic lateral torsional buckling. In this case, there's just two equations that they use. They have this guy right here, right? They have this guy right here, and then they have this guy right here. This accounts for both of these limit states: plastic moment capacity and inelastic buckling. Okay, this one right here is straight up elastic buckling. Okay, if you were to plot that curve on here, it actually goes like this. It goes like, it kind of is a continuous. Okay, it looks something like that. It doesn't have a kink in it, right? This guy's got a kink, goes boom, and then goes down. This thing is just, if you were to plot this equation, it would go like this, right? And when you hit this value, okay, these two converge to be the same point. So they actually meet right here. And then from here, that's a plot of this. Okay? And so this area right here is equation A. Well, let's align to it. So this straight lines is that region. This is this region. Okay? And so this is how the code handles it. Is they say, yep, this is what your capacity is. That's what this curve is right here. If your KL over R is less than 4.71 times square root of E over Fy, then you have either the plastic capacity or the inelastic buckling. You have yielding, right? I mean, it's going to be yielding. Right? You'll either have yielding. These things get lumped together. It's either yielding or inelastic buckling or the two together, right? And then if your K over R is greater than 4.71 squared, then you have elastic buckling, and you use this equation right here. Okay, and then phi is 0.9. I just kind of write those things. Right, I got room for that. I'll put those down here. Oh, yeah, I can just write. I'll write it. So phi. Some notes down here. Note. Phi is equal to 0.9. Okay. Also, we have, just to formalize this, two equations for 3 limit states. Okay. And the last thing I wanted to mention is what that 0.877 is for. 0.877 is to account for initial crookedness. Okay. I think that, so what they did is they ran a bunch of tests and they were comparing Euler buckling to this value right here, and it wasn't working out. Super slender members, and it wasn't working out, and they were always buckling earlier. Okay, buckling on average 87%. At 80%, at 87% of what what you expected them to break at. Okay, or what. They were buckling at a load that was only 87% of what Euler buckling was saying it was. And what they traced it back to was that this, Euler buckling, assumes that all the members are perfectly straight. They are not perfectly straight. They have some initial crookedness. And so then that's why they use this 0.877. So this is just empirical, and it's to account for initial crookedness that's in there. Okay, and so you might be asking yourself, holy crap, look at all these freaking equations, right? What a pain in the butt to try to design one of these things. But keep in mind, for the most part, when you design things in steel, you're going to use standard sections that have certain dimensions and properties and stuff like that. And so there's going to be some design aid that's going to help us design these things, okay? And that's kind of what the next topic is going to be about, is what are these things that are going to help us do these designs, okay? Or what are these design aids? What are the design aids going to be that are going to help us, okay? There's going to be some tables. Then those tables are going to have to take into consideration KL over R. Then it's going to have to take over to KL over R and the different members and how much load you're going to put on it and stuff like that. So that's kind of going to be what our, not kind of, that is what is going to be our next topic, is how do you go about designing these things, okay? But first we're going to talk about column types, and then we're going to talk about design aids. Okay, that's we're going to get down to that at some point. But just got to give you some I'm going to stop right here. Okay, I think this is pretty long. The one of the next topics though is going to be talking about weak axis versus strong axis. As you can imagine, if you just took and applied a load And so imagine this is looking at the side of a wide flange member, okay? That if you apply a load, more than likely it's going to buckle over the weak axis, okay? Or if you have no other conditions there, it absolutely is going to buckle over its weak axis. The restoring force in the weak direction is small, or another way to look at it, the R for the weak axis is going to be smaller. Your radius of gyration is going to be smaller for the weak axis. It's not resistant to bending as much. Okay, and so it's going to buckle about its weak axis. And usually I bring in a yardstick, right? Imagine bringing in a yardstick and applying a load on it, and it's buckling. Is it ever going to buckle along? Right, your intuition will capture this, right? Is it ever going to buckle against its strong axis? No, it's not going to buckle on a strong axis. It's going to buckle around its weak axis, right? And it's always going to be that way. Okay, but what if you took and you started applying supports in the weak axis, right? So in this particular case, right, this thing would buckle out of the page, right? But what if there was a beam that was right here and that was preventing the thing from buckling out in the weak axis, but not buckling it out in the strong axis? And so this thing could buckle right over the strong axis like this, or in the weak direction it could buckle something like this. Okay, which one's going to control? Don't know, right? So that's kind of another limit state that we get added to this. Is it going to be buckling around the strong axis over a longer length, or is it going to be buckling across the weak axis over shorter lengths? Okay, and so that's going to be part of the design that we have to take into consideration. Okay, and then we just do an example. Okay, and this example is pretty straightforward, not difficult to do, and you have a homework that you have to do one of these buckling type problems, and there'll be one of these things on the final exam. So I think that is it for tonight, and then I will post another one tomorrow with a homework, and you guys can work on that homework, and then that's it. Then we're done with new topics. You have a lab final this Friday. Prep for that. Don't not prep for that. Okay, and I think Jaden gave you like a little study guide and stuff like that to kind of flip through and get ready for. And then we have the final next week. All right.